In this series of videos I'm designing a Z80 based computer system. So far I've designed the Z80 core itself, the DRAM controller, the various control circuits that are required to make the system run, so that's memory mapping, bank switching, that sort of thing. And because this will be a full computer system and not just a simple single board design, I've included a fully functional text output system. So we won't need to rely on something like RS-232 to communicate with our computer. Having said that, in this video we are going to look at adding RS-232 to the system. So when I started considering how to go about adding this, I was tempted to use a UART. They were available back in the early 1970s, as early as 1970, 1971, and the problem was that the purpose of this project is to not only design a computer, but to go through the process of how to go about designing a computer. And as part of this project, I'm writing a book that I'll be releasing at the end of the project, where I describe all the internal workings of each circuit. So we're doing the design the hard way, discrete logic where at all possible, avoiding large-scale integration devices, and that includes things such as UARTs. So I decided to design the RS-232 interface using the same techniques, discrete logic, rather than large-scale devices. So because the receive section of a device like this is harder than transmit, I decided that's where I would start. So that's what I've been putting together here. So we've got the receive section of our RS-232 interface, and it looks quite straightforward. It is straightforward, and again, as long as you kind of think through what the circuit has to do, it is quite easy to design one. And a good starting point is to think about the origins of RS-232 and why we have the various elements within the protocol, start bits, stop bits, parity bits, that sort of thing, because they are there for a reason. For the most part we don't need them these days, and they're there really because the RS-232 protocol came about at a time when most devices were mechanical, and the mechanics within the machines required certain timing and certain delays in order to work. We don't really need a lot of these in modern electronics, but they are still there for compatibility because the protocol hasn't really changed. Also, something like a UART, the U stands for universal, so they're generally designed to be usable and configurable within lots of different systems. But we don't need that because we are designing a specific system, and we are designing the circuit to go into a specific system. So we don't need all the bells and whistles and settings. All we need to do is decide which particular settings we're going to use. The only real configurability I'm going to include is the baud rate control. So this does include up to 8 different baud rates, and it will support hardware handshaking as well if required. So you might be wondering how we get all this into such a simple circuit. And in fact, this circuit also contains the tri-state buffer, so we can interface this to the Z80, the interrupt outputs, so it will generate an interrupt line, interrupt signal when a data packet has been captured, and the device in the middle is actually a line driver, so this or line receiver, so this also contains several devices that you could get rid of. It's only 5 devices, but at least one of those you could get rid of if you wanted to, and the other buffer is only there because we will be connecting this directly to the data bus of the Z80. So it's quite a simple circuit, as you can see, and I'll briefly explain how this works. So a starting point is to have a quick look at the RS-232 protocol itself. So this is an example of an RS-232 data packet, and like with the PS2 that we looked at, the data's sent in data frames, and they do vary in length depending on the configuration that you're using, whether you're using parity, 1 stop bit, 2 stop bits, whatever. The format I've decided to use is, we obviously have a start bit, we'll have 8 data bits and 1 stop bit, and that's going to give us all the functionality we need within our system. As I say, we're not designing a UART, we're more kind of designing an art, and it's up to you if you decide to just use 7 bits. You could simplify this circuit even further if you only needed 7 bits. And the way we're going to go about designing this, and a lot of circuits I see for this sort of thing are over complex, and you can use similar techniques to what is actually used within the internal workings of a UART. And the starting point for this is literally the start. And if we look at the way that this data packet is structured, they always start with the start bit, obviously. And that start bit, and the one thing you have to bear in mind is that the data is inverted on most RS-232 links, so just make sure that you get the right orientation for the bits. But assuming we have the data in this format, then the start bit will begin with a rising edge. And an important aspect with the RS-232, in fact 2 important aspects, is there is no clock. It's a single wire protocol, and so you have to recover the clock yourself, and that generally means oversampling the data, so you take more than 1 sample per bit, because you can't use the same sample rate as the expected baud rate, because your local system is not synchronized with the remote system. So in other words, these edges can occur anywhere within the expected time period relative to your local machine, because your local machine has got no knowledge of the clock of the remote machine. So generally you'll oversample, and that will allow you to determine where within each bit period to sample the data. And also the second point is the RS-232 protocol is a non-return to 0 protocol, which means that if, for example, here we have 2 consecutive high bits, there is no return to 0 between them, so there's no edge, no data edge. So we can't rely on data edges to interpret the data. So we have to sample the data at a suitably high rate to make sure that we can properly capture what the data is supposed to be. There are of course errors in the data rates, the crystal or the oscillator at the source end, and at our end it won't be perfect. There will be errors introduced because of that, and also because we will be sampling this using a finite clock speed. That in itself will introduce errors, because obviously we don't have an infinitely short time between those clock edges. So the higher the sample rate, the smaller the error is that we can effectively zero in on. And the way we're going to actually run this is, as I said, to use the start bit, and we're going to use that start bit to trigger our circuit into starting to capture the data. It's then going to start shifting data at a predetermined interval, and that will be based on our clock frequency that we're feeding into this, and we'll sample the incoming data at a high enough rate to minimize the error, and again the error will accumulate through the packet. What we'll then do is we'll use this start bit, and this start bit, if you think about it, is going to make its way through our shift register. We're going to use a shift register to capture the data. So when the circuit is triggered, it will start shifting the incoming data bits into the shift register. There will be 8 data bits. It's an 8-bit shift register. So we've got 8 data bits plus the start bit, which means this start bit will end up being shifted out of the end of the shift register. And we can use that, knowing it's always going to be high, to actually stop the process. In fact, what we have to do is extend our shift register by 1 bit, and we can do that by just adding a flip-flop. It's all really shift registers are internally. They're a series of daisy chain flip-flops. So we can add one more to the end of this, use the most significant bit as the data source for the flip-flop, clock it from the same clock we're using to shift the data, and that way we can effectively look for the start bit coming out of the end of the sequence, and then we can stop the sequence, stop capturing data, and that will be the data packet captured. If we don't stop the shift register from clocking data, then obviously it's just going to push all this straight through the shift register before our computer gets a chance to read it. And of course we need to generate a signal to tell the Z80 that data has been captured. Okay, so that's what we're going to do. In terms of sampling, then we've got a division ratio that is variable. The baud rate is settable on this, but it's as a minimum we're going to use 16 clocks as our oversampling rate, and that will increase depending on the baud rate. And in fact, with the baud rate I have selected here, which is 9600, our oversampling ratio is actually 64 clock cycles per bit, so we've got a very good resolution on our sampling. So what will happen is when the data starts to come in from our remote connection, I've got it connected to a PC that's running an emulator, and we can send it some RS-232 data. It will come through. We've got a line receiver that will translate the RS-232 signal into TTL. That will trigger the flip-flop. That will tell the counter to start counting. The counter generates the required clock signal. The first interval, the first sample period, because the counter will start at this point, the first sample is actually half a bit period. So it samples halfway through the start bit, and thereafter it's a full bit period. So we need to take that into account with our circuit. If we don't do that, we'll be sampling on the edges of the bits, and we'll get all sorts of weird behavior because it will be kind of a race condition between each bit. So we need to make sure we're sampling towards the center of each bit period. We then sample each of the expected bits, shift them into the shift register, and then when the start bit appears at the end of our daisy chain, we stop the process. In our circuit here we have the counter, an 8-bit counter. The first design of this was actually 2 4-bit counters cascaded, but I changed it just to reduce the IC count by 1. We've got a dual flip-flop, so there's one used for the start bit, one used for the stop. Again, very similar to the way the mechanical systems used to work. We've got a shift register at the top underneath these jumpers. We've got the line receiver, and then we've got an 8-bit latch with tri-state outputs. So this will operate in a similar way to our PS2 interface, in as much as when it captures some data, it will generate an interrupt out line, and that will illuminate this red LED at the bottom left here, and then we'll see the data appearing on the blue LEDs when we try to read the data. So initially we won't see the data because the latch output is normally disabled, but when we enable the latch by taking the latch enable line or output enable line low, that will show the data that's been latched, and it will also reset the circuit so it's ready for the next incoming data packet. If we want to, we can also use the control output, the stop bit output from the flip-flop to connect through to a line driver and provide hardware handshaking, so it will prevent any more data coming in until the Z80 is ready. As this circuit is configured now, it will just ignore any data after the first data packet's arrived until the circuit is reset. Now in reality the Z80 will be running so quickly relative to RS-232 that it should be easily able to handle the incoming data without needing handshaking. But we can of course implement handshaking either in hardware or we can use X-on X-off hardware if we want to, handshaking if we want to. Okay, so what I'll do now is I'll go and send a character from the remote terminal, and we should see the red LED illuminate to tell us that some data has been received, and we should also see some data appear on the scope. I'll explain what the scope is looking at once we've received the data. So as you can see, the LED has come on, we've captured some data, and you can also see hopefully on the scope that we have got some signals. Now the top yellow trace is the incoming data, the blue trace is the shift register clock, so that's essentially our sample point, and hopefully you can see that the rising edge of the clock, which is the point at which we shift data into the shift register, is right in the middle of the bits. So it's right in the middle of the start bit, it's in the center of the first data bit, and then it's in the center of all the subsequent bits. The bit at the end here is the last data bit, that's bit 7, and again you can see that the rising edge is fairly close to the center, so we haven't accumulated too much of an error, and the system then stops, it halts the clock that's shifting data into the shift register, prevents it being shifted any further. And so we've successfully captured some data. The green trace is the inverse of our interrupt line. So the interrupt line will actually go low, but I'm looking at a slightly different part of the system, so it's showing us high on here, but that's the point at which the interrupt line is toggled to inform the Z80 that there is some data. The Z80 will then come back. This line here is the read line. This will do several things. It will enable the tri-state buffer, so it will tell it to put the data onto the Z80 data bus, which is represented here with these blue LEDs, and it will also reset the two latches. It will reset the shift register. The shift register does of course have to be cleared in between each byte, because we need to make sure the first high bit coming out of it is the start bit for the next packet, and we also need to clear the counter, and the counter needs to start off with 0, otherwise when we get to the first edge, when it wants to sample the data, if it hasn't started at 0, then there'll be an offset and we'll get random behavior. So we'll try and read the data. So we'll take this line low, this is the read line. This would normally be connected to the in-out port of our Z80. Take this low, and you can see that it's reset the interrupt line, and also we've got the data here. So this was an uppercase A, so it's showing us 41 hex. It's actually inverted. The latch I'm using is a 74LS374. It's a non-inverting latch. I have got some identical devices apart from they invert the data on order. I didn't have any in stock, but it will operate in exactly the same way, except that it will invert the bits when they're put onto the data bus. It will just save the Z80 having to do it itself. But if you just imagine these inverted for now, we've got 4 in the left hand, the most significant bit on the left here, and so that's 4 and a 1, 41 hex, that's an uppercase A. And if we then raise the read line, so the read would obviously occur very quickly within the Z80 read cycle, this would then go back high, disables the latch, and the system's then ready to capture the next bit. So I'll go and I'll send a B this time, and we should see that reflected in the data that we capture. I'll rearm the scope so you can see it capturing the next byte. And as you can see, we've successfully captured the next data. Timing again is correct, and if we now try and get the Z80 to read the data, it should reset the circuit and we should see the data appear on the output. And again, it's correct. This time it's showing 42, which is the correct ASCII value for an uppercase B, which is what I sent. So as I said, this is adjustable in terms of the baud rate. All we have to do is select a different division ratio for the clock. So if we change it, I'll go from 9600, which is what we're now at 19,200. And if we look at the scope, and I won't change any scope settings other than to rearm it, and I'll go and send the same character again, and hopefully you'll see the difference. So as you can see, we've got twice the baud rate. I changed the terminal settings so it was set to 19,200, and we'll try one more baud rate. I'll reset the circuit. We'll just check to make sure we've got the right character. It should be the B. So again 42, which is what it should be. So we'll go to the next baud rate up. This will be 38,400. Rearm the scope, and I'll go and send the character. So as you can see, the rate has doubled again, and we'll check we're getting the correct character, which we are. And this time we'll go the other way. I'll go to a much slower baud rate. We'll go down to 4,800. I'll change the time base on the scope so that we can capture the data packet. And I'll go and send the character. So once again, we've captured the data. We'll check we're getting the correct value, which we are. So you can see it's very easy. We can change this current configuration will let us select anything from 2,400 baud up to 38,400. So it's very flexible. In fact, it will go beyond that, but we wouldn't normally choose anything higher than that for this type of device. So very simple circuit, but very effective. It's very reliable, so you can see it samples very nicely, and because the oversampling is also automatically adjusted when we move the jumper, it's effectively self-corrects, and we make sure we always get the correct data coming through. So with the baud rate setting, there are two ways we can go about implementing the adjustment on our final system. All we're really doing when we change the baud rate is moving this jumper, and this selects the division ratio for our counter. And all we're really doing is connecting it, of course, to one of the outputs of the counter. So we can either have a series of jumpers, one jumper and a series of headers on our board, and move it whenever we want to change the baud rate. But if you wanted to implement the system so that you could change the baud rate under software control in a similar way to UART, very straightforward to do. All you would need is a 8-to-1 multiplexer. The output would go to the clock, and the inputs will be connected to the various outputs of the counter, and then you would have a latch that controls the selector lines of that multiplexer, and you could then connect that to, for example, an in-out port of the Z80, and the Z80 could then write a value into the latch that would select the appropriate channel for the clock, and you would then have the ability to change the baud rate under software control from your Z80. So I may well implement that when I put this onto a PCB. I won't do it now because, as I said before, making the complex layouts on breadboards tends to end up with very large breadboards. But hopefully you can see that with a very simple circuit we've got a lot of functionality. It allows us to capture the data reliably. It allows us to control putting that data onto the Z80 data bus in such a way that the Z80 can read the data using a standard memory read operation, and it also allows us to generate the interrupt required to flag to the Z80 that we've actually received some data. And we're doing all that with just 5 ICs, and that includes the line receiver. So that keeps our overall IC count fairly low. We will now need, of course, to move on and create the transmitter side of our RS232 link. But the transmitter side is normally a lot easier to arrange because we don't have to concern ourselves with the oversampling. We can just make sure we send the data out at the correct rate, and that's obviously a fairly straightforward thing to do. Okay, well, hopefully you found that of some interest. The receiving part of the RS232 module is now complete. The book goes into far more detail about this and how it works. Gives the schematics for both the dual 4-bit counter version and this single 8-bit counter version. But as you can see, you can do quite a lot with just a few ICs, and this gives us the exact functionality that we require for our system.